Welcome to Mastering Solutions. Since we have this light emitted by this whatever element this is, they say that there are several wavelengths that are emitted by it, and we don't know what they are. That's what we're trying to solve for. Because they tell us that all of them are first order maxima, m is going to be 1 for all of them. And so since they're all first order maximum, and we also have multiple different of them, that's how we know that there's different wavelengths. So let's keep going with our list of things that they tell us in the problem. We're told that the diffraction grating has 1200 slits per millimeter. So D is the diffraction grating slit spacing. And as always, it's the width over the slits or the lines. And in this one, we have 1 millimeter. So 1 times 10 to the negative 3 meters over the slits is 1200 slits or lines. Now I'm going to leave it like this. And they tell us that L, or the distance of the viewing screen from the diffraction grating, is 75 centimeters. So that's 75 times 10 to the negative 2 meters. We're told that Y is several. So we have 56.2. So 56.2 times 10 to the negative 2 meters. We also have 65.9 times 10 to the negative 2 meters. And we also have 93.5 times 10 to the negative 2 meters. And as we said already, they're all going to be m is 1. So now let's think about how we're going to solve this. And we'll use two equations. We've used them a lot on the past few problems. The first one is y is equal to L tangent of theta. This one is going to be an intermediate equation because we're also going to be using the equation sine of theta is equal to m lambda over d. Now remember, what are we trying to solve for? We're trying to figure out what are the different wavelengths. And in this case, we'll have to do this step multiple times, or the problem essentially a few different times. We're trying to solve for lambda, so let's isolate that. We'll multiply both sides of the equation by d, and then we'll divide both sides of the equation by m. So the d's will now cancel and the m's will cancel. So now we have d over m times the sine of theta is equal to lambda. But we don't have any thetas, and so that's why we have to use this equation to solve for theta, and then we plug it into here to give us our wavelengths. Now you could do this in two steps. You could do one step here and then plug that answer into here. I'm going to combine the two equations so that there's less work we have to do in the calculator, less room for error. So let's isolate theta. And so we're going to divide both sides of the equation by L. That gives us tangent of theta is equal to y over L. And then we take the inverse tangent of both sides of the equation. So we have theta is equal to the inverse tangent of y over L. Now we can plug this in to this equation. So our final equation is going to be lambda is equal to d divided by m times the sine of theta, which we said was inverse tangent of y over L. Now, this is the full equation. You could simplify it even one step more if you want, because all of the m's are 1. So you could also write it like this: d sine theta, or not sine theta, sine, and theta is tangent inverse y over L. This is just because of m equals 1. So if we had other maxima that weren't 1, then we would use this one. So don't let this step confuse you. So now let's give us some more space. And as we've done on a lot of problems, I'm going to plug in the numbers into the equation. And then in the calculator, I'm just going to replace the y for the three different ones because that's the only thing that's changing. So we have lambda is equal to d, which we said was 1 times 10 to the negative 3 meters divided by 1200 slits. And then we don't have to worry about m, but we can also put 1 there. And then we'll times that by sine, and then inverse tangent. And then y here, this is the one that will change. But for the first one, we have 56.2 times 10 to the negative 2 meters. You can also move the decimal place over 2, so 0.562 if you want. I like to do this because there's less room for error. You don't have to wonder if you move the decimal place incorrectly or not. You just change the prefix, in this case centi, for what it means, 10 to the negative 2. And then we are dividing that by L, and in this case, L was 75 times 10 to the negative 2. So for the first y, and we'll say 56.2, what does that give us? So we have 1 times 10 to the negative 3 divided by 1200. 1200 times the sine, inverse tangent, and then we have y. In this case, we have 56.2 times 10 to the negative 2 divided by L, and that L we said is 75 times 10 to the negative 2. So our first answer in this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So the first wavelength is 500 nanometers. So that's kind of a greenish color. And then the second one, we'll do Y for the 65.9. Now we can just copy our equation down and just go back and change just the Y. And we said it was 65.9. And so now we have 550 nanometers. And just for time, I'm going to just do the last one. And then we had 93.5, and we have 650. So we have 500, and then we have 550 nanometers, and then Y of the 93.5 was 650 nanometers. So these are the three wavelengths that are produced by the element in this question. And we did that by finding the angle for them and then plugging it in to solve for lambda.